All right, guys. Hi. Sorry, I'm gonna move on up to over here. All right. So in this video, we're gonna be going over the KSP dry lab slash lab quiz. So this is school year 2024-2025. So this video is for this year for the students who just took this assessment as a quiz, uh, as a summative grade, and it was a collaborative test. If you're watching this in future years, this would be your practice quiz that you might get a copy of and be working on before you take the actual quiz. So in this video, we're going to go over this. So this is it's a dry lab. So you have the lab data. It's given to you. So what are the different calculations you're going to do with those measurements? But it was a lab quiz because this was a summative grade. Now we made it collaborative, so you guys were working together. But this is, probably one of the more difficult questions you'll see this year because you got to take a lot of concepts that we've covered and kind of combine them and tie them together. And that's number one. And number two, this quiz maybe should take 30 minutes max. And you were given 50 minutes in class, and a lot of you were running out of time. So I don't know if it's because you weren't taking it as seriously as you should because it was collaborative and you were more social than you were actually focusing on the test. But let this kind of be a wake-up call of how fast you have to be able to process things, recall things, tie things together, make those connections. And half the battle is the speed, right? A lot of you would probably have gotten to the right answers eventually if you were given a couple hours to think about this stuff. But you don't get that on the AP exam. It's a very hard time crunch, and you have to work fast. Okay, so I'm going to go through this and show you kind of different ways you can think about it, and show you the right answers and show you the right calculations. And so hopefully it'll be helpful, and hopefully you'll lock in and you'll sign up to come and retake it. And yeah, the retake's going to be very similar, just different compounds, but the same idea, right? So let's jump into it, right? So in both these questions, question one and question two, the only one that's kind of an outlier is question 2C, but we'll get to that in a second. The purpose of the lab is to determine the KSP of a salt. So in question one, we need to find the solubility product of calcium hydroxide, right? And if we look at question two, the goal is to figure out the solubility product, which is KSP, of another ionic compound, aluminum sulfate, okay? So, the train of thought you should have is, okay, I need to find the solubility product. What is that? What information do I need to actually calculate a value for a solubility product? And then, how can I use this lab data to figure out those values, the values that I need, right? So let's walk through it. Whoops, I hit the wrong thing. All right, here we go. All right, here we go. All right, so let's look at question one. We need to find the KSP of calcium hydroxide, right? So let's understand what we're talking about. A solubility product is the equilibrium constant that shows the salt in question. So in this case, the calcium hydroxide dissolving in water. So here's the equation that's happening, all right? So you got calcium hydroxide, salt, solid, yields one calcium ion and two hydroxide ions, right? So the KSP will be equal to the equilibrium expression of this reaction, and that would just be the calcium concentration times the hydroxide concentration squared, okay? And then what we have to recall is, all right, for any ionic compound, any salt, if you know one of these four values, you should be able to calculate all of them, right? So what are those four values, okay? Obviously, for this question, it's not going to be KSP because that's what we're trying to get to in the end. But in order to calculate the KSP, if we could go from the lab data and figure out the molar solubility of the compound, we could figure out the KSP. If we could figure out the molarity of calcium at the point of saturation, then that would be the concentration of the cation. or if we could use the lab data to figure out the molarity of hydroxide, right? So let's understand what this means, right? If I find the molar solubility, that's the molarity of this entire compound. And if I find the molarity of this entire compound, I could plug that into my KSP shortcut and for this particular salt. And remember, in the shortcut, S or X, for this one, it would be KSP equals 4X cubed, or 4S cubed, if you want to call that. When you solve for that unknown, when you solve for S or you solve for or S or X in that shortcut is the molar solubility. So if you find the value of the molar solubility of the compound, you could plug it into the shortcut and you could solve for the KSP. The other thing you could do is, if you know the molarity of the entire compound, well, it's got a 1-to-1 ratio with calcium, so that would be, the molar solubility would be the molarity of calcium, but 2 times the molar solubility would be the molarity of hydroxide, right? So we can find the molar solubility and use the molar solubility to get this concentration and that concentration, plug them into the expression and solve for the KSP. We could plug in the molar solubility into the KSP shortcut, in for X or S, however you want to memorize the shortcut. KSP equals 4X cubed, plug in the molar solubility for X and solve for the KSP. That's another way to go about it. If I know the molar solubility, I can figure out the concentrations of these ions. Or if I use the lab data to figure out the hydroxide concentration, then all I would have to do is divide that by 2, and that would give me the calcium concentration. And now I have both of those, and I could solve for the KSP. And then also I could recognize that since calcium and the entire compound have a 1-to-1 ratio, the molarity of the calcium ion in this instance would be the molar solubility of the entire compound, right? So we got to make those connections. All I need to do is figure out one of these values to get to the KSP. Now the question kind of breaks it down, and it asks you for this concentration and then that concentration and then the molar solubility and then the KSP value. But you can do it whatever order you want, right? Our goal from this lab is to figure out the KSP. I can figure out the KSP by figuring out one of these values from the lab data, okay? So again, for this question, right? So understand, if you know the KSP, you can also solve for these, but the purpose of this lab was to figure out the KSP. So we're going to use the lab data to figure out one of these values, so then eventually we can solve for the KSP, right? Okay. So again, for this particular question, we need to find the KSP. So we need to either take the lab data to figure out the molar solubility of calcium hydroxide, okay, or use the lab data to figure out the calcium concentration, if that's possible, or use the lab data to figure out the hydroxide concentration in a saturated solution. And again, as soon as I find one of these 3 values, I've unlocked them all, and also the KSP, okay? So let's go back to the question. All right, so what lab data did we get, okay? And we'll, we saw the balanced equation, we saw the expression, but again, we'll go over all the answers here towards the end of question 1, okay? So we did a titration. So we had a saturated solution of calcium hydroxide, and we started with 10 milliliters of the solution. So we know the volume of the solution, we just don't know the molarity, right? We titrated it with HCl, and so imagine if we're doing a titration lab, right? We started with HCl in the burette, and the initial reading was 1.12 milliliters. We slowly added the HCl to the calcium hydroxide until we reached the equivalence point, or the end point of the titration, and the final reading was 22.61, okay? We're also given the molarity of the HCl that we used. So if we do final volume minus initial volume, that's going to give us the volume of HCl. We know the molarity of HCl. So now we can figure out how many moles of HCl were required to react with this volume of calcium hydroxide. So it's just a titration stoichiometry calculation, okay? So if we want to use stoichiometry, this is how we're going to find the molarity of calcium hydroxide, okay? Which would be the molar solubility of calcium hydroxide in a saturated solution, okay? So if we go back here, okay, if we find the molar solubility, okay, we can plug that molar solubility of calcium hydroxide into our KSP shortcut. That's the molar solubility. So once I figure out what this number is, I plug it in, I cube it, and I multiply it by 4, and I got my KSP, okay? So it's just stoichiometry, acid-base stoichiometry. Okay. So the first way would be, okay, here's our balanced equation. We need two HCl's for one calcium hydroxide. Remember, the acid has one H plus, the base has two hydroxides, so it's going to be two acids for one of the calcium hydroxides. That's going to give us calcium chloride, which would stay aqueous, most likely. Maybe if it gets concentrated enough, it could precipitate out, right? And you could do a whole other question about QSP and KSP and will this precipitate or not, but that's not the point. And then we go water, all right? So the key is it's one calcium hydroxide for every 2 moles of HCl. So to figure out the volume of the HCl used, we do our final minus our initial volume, and we get 21.40. Remember, that 0 is needed when you report your answer because when you subtract, it's about decimal places. So we have 2 decimal places, 2 decimal places. My answer needs 2 decimal places. So it's that many milliliters of HCl. Okay. Now we'll take our liters. So all this number is 21.40 in liters. Liters times the molarity of HCl, which was given to us on the quiz, will give us moles of HCl, but the mole ratio of calcium hydroxide to HCl is 1 to 2. So we multiply by 1, divide by 2. And that'll give us moles of calcium hydroxide in the 10 milliliter solution of calcium hydroxide. But I want to know the molarity. I want to know the molar solubility. So if I take moles of the compound and I divide it by liters of solution, where did this number come from? It was 10 milliliters of calcium hydroxide. So that's 0.01 liters. So the moles of calcium hydroxide divided by its volume in liters gives me the molarity. So this is the molarity of calcium hydroxide from the lab data, which is the molar solubility of the compound. So all I have to do is if all I needed was the KSP value and the quiz didn't ask me about the other concentrations, I could just plug this in to my KSP shortcut, right? Just plug it in there. So what was it, 0.0107 cubed times 4 would give me my KSP value, okay? But also understand what we just unlocked, right? We have the molarity of the salt, and if we want the molarity of each of the individual ions, the molarity of the entire compound times 1 would give me the molarity of calcium when it's saturated, which is the equilibrium molarity or the saturated concentration. And then 0.0107 times 2, because there's 2 hydroxides for every one of these, would give me the molarity of hydroxide at equilibrium, right? So instead of plugging this into my KSP shortcut for X and solving for the KSP, I could plug this concentration into the equilibrium expression and this concentration and then square it into the equilibrium expression, right? And that could give us our KSP, right? So again, solve for the KSP this way, 4 times the molar solubility cubed, but it would really be the molar solubility cubed times 4, or the concentration of calcium times the concentration of hydroxide squared. Okay, either way, we get the same value of the KSP. Okay. Now, you might be thinking that, well, wait a minute. In acid-base titration, I didn't use stoichiometry back in Unit 2. I used the shortcut, MAVA equals MBVB. And you could do it that way. But you got to be careful because, what are you solving for? I'll come back to all the answers here in a second. The other way we could have taken the same lab data, okay, and calculate the molar solubility is if we did MAVA equals MBVB, if we doubled the base side because the base has 2 hydroxides and the acid only has 1 H plus, when we solve for MB, it would be the molarity of the calcium hydroxide. So it would be the molar solubility. So notice when I plug those numbers in to that shortcut equation, I get the same value for the molar solubility. Okay. However, if you forgot that shortcut, like if you forgot that you have to adjust the shortcut depending on how many hydroxides your base has versus how many H pluses your acid has, right? And you just did MAVA equals MBVB. Understand this, when you use this equation, but you don't double the base side, when you solve for MB, that would be the molarity of hydroxide because this is really H plus, OH minus, OH minus. It's a 1-to-1 ratio. And so if you don't adjust this equation, then when you solve for MB, that's going to be the molarity of hydroxide. Okay, and notice if I plug in the numbers here, but I don't double the base side, I end up with 0.0214, which was our answer for the hydroxide concentration. Okay. All right. So, so again, right? Let's go through the answers of the quiz. So we got to be able to show a salt dissolving in water with states of matter. Okay. You got to make sure we can look at this and say two hydroxides and put that coefficient 2 in front of the hydroxide. We have to be able to write the KSP expression. Okay. And then taking the lab data, so figuring out the volume of HCl, we subtract, get the volume of HCl. Okay. And again, if I did MAVA equals MBVB, but I didn't double the base side, that would give me the hydroxide concentration. The volume of the base would be 10 milliliters. The volume of the acid would be 21.4, and the molarity of the acid is 0.01. So you could solve for molarity of the base, but in that case, if you didn't double the base side, you would get hydroxide concentration, and you would have to know to cut this in half to get the calcium concentration. And then you could plug these two numbers in to the KSP expression to solve for the KSP, or you could recognize that this right here, that number, the 0.0107, is the molar solubility, and you could cube this and then multiply it by 4 and get the same value. Okay. So in part D, the student's doing the same thing, trying to figure out the KSP value of the calcium hydroxide, but instead of doing a titration, they just measured the pH of the solution. Okay. And so what we have to remember is, okay, well, calcium hydroxide is a base. pH is a measurement of how acidic a solution is, but so is pOH. And so what we could do is we could do 14 minus the pH to get the pOH. And if we know the pOH, we can calculate the molarity of hydroxide. So from the pOH value, we can calculate this number. And then if that's the molarity of hydroxide, the molarity of calcium is half of that. And then plug them into the expression. Okay, but this is a student using different data, so their KSP value might end up being a little bit different than the student who did this procedure. So let's see what happens. Okay. All right. So we're trying to find the KSP, okay, but we have the pH of the solution, right? So if we know the pH, we can figure out the H plus concentration. That doesn't help us here. But if we know the pOH, we can determine the hydroxide concentration. So we're going to do 14 minus the pH to get the pOH. So the pH was 12.333. So the pOH comes out to be 1.667. Okay. Now, how do you go from the pOH to the hydroxide concentration? Okay, well, pOH is equal to the negative logarithm of the molarity of hydroxide. So if you solve for the molarity of hydroxide, 10 raised to the negative pOH value will give you your molarity of hydroxide. So here's our pOH value, 10 raised to the negative that number, so 10 raised to the negative 1.667 will give me my molarity of hydroxide. So notice it's a little bit more than the titration lab that they did, but that's okay. We're using this student's data, okay? So according to this student's data, this is the molarity of hydroxide in a saturated solution. We could divide this by 2 to get the molarity of calcium, but also if we divide this by 2, it's going to be the molar solubility of the entire compound. Okay, so we could divide this by 2 and plug it into our KSP shortcut as the molar solubility and solve for the KSP, or we could divide this by 2 and plug the calcium concentration and the hydroxide concentration into the expression to calculate the KSP. Either way is fine, whichever one works best for you. Okay. So if we divide it by 2, we'll get the calcium concentration. Also, if we divide it by 2, it's the molar solubility. It's the same number. So, if I divide by 2, technically I should say 0.0108 here because I should only have 3 sig figs, okay? But you can keep it there and then round at the end, and it might be a little bit different than if you did it the other way, okay? Or you could use the expression. So here is the concentration of calcium. Here's the concentration of hydroxide, and this should say squared. It's cubed here because I was using the shortcut. I was like, what did I do? No, that should say squared. Either way, this is the right value, and that should say squared. I apologize for that. Always a typo. I apologize. Okay. Okay. So that's question 1, right? So let's go back and make sure we review the answers for question 1. Okay. And again, this one was close. It came out to be 4.99 times 10 to the negative 6, whereas student number 1 found 4.90 times 10 to the negative 6. Okay? All right. So question 2, very similar question, but it's not really acid-base chemistry. So we're not going to use acid-base stoichiometry or pHs or pOHs to determine concentrations. But again, we're asked to find the solubility product, again, which is KSP, not molar solubility. But if we could figure out the molar solubility, then we could plug it into the shortcut and solve for the KSP, right? But we're asked to find the solubility product of aluminum sulfate. Now, a couple things to just note right off the bat. This has a different ratio of ions. So if we wanted to use our KSP shortcut, figure out the molar solubility, plug it in for X or S, and solve for the KSP, it's not going to be KSP equals 4x cubed like the previous problem. Remember, when you have a 2 to 3 ratio, the shortcut is KSP equals 108 x to the fifth, where X or S, whatever you want to call it, is the molar solubility. All right. So if we could figure out the molarity of this compound when it's saturated in solution, that would be the molar solubility to plug into that shortcut to solve for the KSP. It's just going to be a different shortcut because we have a different ratio of ions. Okay. But again, our whole goal is to calculate the KSP for this salt, right? So let's again describe what that means. All right. So we got aluminum sulfate. So just like before, let's write the equation that this is going to represent. So we got aluminum sulfate yields 2 aluminum ions plus 3 sulfate ions. Okay. The KSP expression would be KSP equals aluminum ions squared times sulfate ions cubed. And our KSP shortcut, where this is the molar solubility, would be KSP equals 108 x to the fifth. Okay? So if I can figure out these two concentrations, I can plug them in and solve for the KSP. Or if I can figure out the molar solubility. Now, this concentration is not going to be equal to the molar solubility. Like the calcium concentration was the molar solubility of the compound because its subscript was 1 in calcium hydroxide. But for this compound, since the coefficient or the subscript for aluminum is 2, and the coefficient or the subscript for sulfate is 3, neither of these molarities will be the molar solubility compound. If I could figure out the aluminum concentration from the lab data, I would have to divide it by 2 to get the molar solubility of the compound to plug into the shortcut. Or if I figured out the sulfate concentration and divided it by 3, that would be the molar solubility to plug into the shortcut to solve for the KSP. Okay? All right. But again, that's our goal. We got to figure out the KSP value. So we're going to have to figure out this number and plug them in, or figure out what that number is and plug it in. Okay? Now, for this data, probably the easiest way to go is using the data to figure out the molarity of the sulfate in the aluminum sulfate solution. And then once I figure out the sulfate concentration, times 2 divided by 3 would give me the aluminum concentration, or the sulfate concentration divided by 3 would give me the molar solubility, right? But just like the previous problem, you're probably going to have to calculate the sulfate concentration, calculate the aluminum concentration, maybe also calculate the molar solubility, and then calculate the KSP. But it's just, you just need to unlock one of those 4 values to unlock them all, right? That's it, right? That's the goal, all right? So what do? They took 20 milliliters of the aluminum sulfate saturated solution, so it's at equilibrium, and they flooded it with barium nitrate. And we should know that barium and sulfate are then going to precipitate out a solution. So they used an excess amount of barium nitrate to ensure that all the sulfate precipitates out. They filtered and masked the precipitate to figure out moles of the precipitate. And all the sulfate is now in the precipitate, so if I can figure out moles of the precipitate, because there's 1 sulfate and 1 barium sulfate, then moles of barium sulfate would be moles of sulfate, and all of that came from the 20 milliliter solution. So all I would need to do is, once I figure out moles of sulfate, divide it by 0.02 liters, and that would give me the molarity of sulfate in our saturated solution of aluminum sulfate. And then once I have that, I can use stoichiometry to figure out that and or the molar solubility, and I can find the KSP. All right. So again, let me go back to the question to illustrate it a little bit more, right? So what they said is they took 20 milliliters of the aluminum sulfate solution and they flooded it with excess barium nitrate. We don't care about the nitrate, right? Nitrate's usually just a spectator ion. Okay. Now be careful. This happens sometimes on the AP exam. They give us the mass of the filtered paper and the precipitate, but then they give us the mass of the filtered paper and the dried precipitate. Which should you use? You should use the dried one, because if you use this mass instead, then that's implying that some of that mass is water and it's not all the precipitate, and then you would overcalculate your moles of sulfate, and you would get a higher concentration for sulfate and a higher concentration for aluminum and all that stuff. Okay. And they were friendly enough to throw in the molar mass for barium sulfate, so we don't have to worry about calculating that. And also, they tell us what the precipitate is. So you don't need to have your solubility rules memorized, but you should remember, the key ones. Barium sulfate precipitates, aluminum chloride precipitates, lead chloride precipitates, right? So all those common precipitates you should have a lockdown on, but it tells you here, okay? So what we're going to do is this number minus this number to get our grams of precipitate. Then we'll do grams of precipitate divided by the molar mass to get moles of precipitate, and times the ratio of sulfate ions in barium sulfate to get moles of just sulfate. All of that sulfate came from this solution, so to get the molarity of sulfate in that solution, we would take moles of sulfate that was in the barium sulfate and divide it by this volume of solution in liters to get its molarity, okay? So let's see it in action. So I would do the mass of the filter paper and the dried precipitate minus the mass of the filter paper. That gives me the mass of the precipitate, which is barium sulfate. That divided by the molar mass of barium sulfate gives me moles of barium sulfate. I understand that it's a 1-to-1 ratio, 1 mole of sulfate for every 1 mole of barium sulfate. And then to convert it to a molarity, I divide by what its volume was in liters. And that gives me the saturated concentration of sulfate in this solution. Okay, so a couple ways I can go about it. If I divide this by 3, that's going to be the molar solubility of the compound, because it's 3 sulfates for every 1 mole of the compound. If I multiply it by 2 over 3, 2/3, that'll give me the molarity of aluminum in a saturated solution, because you get 2 aluminums for every 3 sulfates. Okay, so I have the molar solubility. So I have the molarity of sulfate, I have the molar solubility, I have the molarity of aluminum. Okay, if I wanted to use the shortcut, I plug in the molar solubility into the KSP shortcut. Okay, solve for the KSP. Or I plug the aluminum ion into the expression, but I can't forget to square it. And then I plug the concentration of the sulfate ion, and don't forget to cube it. Okay, so either way, we get 1.99 times 10 to the negative 8 for our value of the KSP for aluminum sulfate. Okay? Okay. So let's review those answers before we get to that last question, which we need this value to answer the last question, but it really has nothing to, it's just a throw, not a throwaway question, but just, throw it on there to test to see if you understand the common ion effect. Okay, so the precipitation reaction was barium ions plus sulfate ions yield barium sulfate. So aluminum was a spectator ion and nitrate was a spectator ion. Okay, right? How do we get this mass? We did this minus the 0.05, and then again I showed you the stoichiometry, but we would do this mass divided by the molar mass. That gives us moles of barium sulfate times the 1-to-1 ratio to get moles of sulfate, and then divide by 0.02 liters to get the molarity of sulfate in this solution. If we multiply this by 2/3, that gives us the aluminum concentration. If I divide this by 2, I get the molar solubility, or if I divide this by 3, I get the molar solubility. Same thing. And then this was our value of the KSP. Okay. So here's our answer for part C, but let me show you how we get there. Okay, so part C is a common ion question. So we know the KSP now. Now we know the solubility product of aluminum sulfate. And now the question is what's the molar solubility of aluminum sulfate when you dissolve it in this solution? So what this molar solubility represents is the molar solubility of the compound just dissolving it in water with nothing else in it. Now we're dissolving aluminum sulfate in a solution of aluminum chloride. So this is a common ion question. So we're dissolving aluminum sulfate into an aluminum chloride solution. So the common ion is aluminum 3 plus. So understand one thing. If you're dissolving a salt in the presence of a common ion, the solubility is going to decrease. It gets less soluble, okay? So I know that my answer to part C should be less than my answer to part, 4 here, okay? This is the molar solubility in pure water. If I dissolve in the presence of a common ion, my molarity is going to decrease, okay? My molar solubility is going to decrease, okay? So if you're asked to find molar solubility and it's no common ion, you should just go to your shortcut and solve for x. You say KSP equals 108 x to the fifth in this situation, and if you know the KSP value, you plug in the KSP value and you solve for x, and x is the molar solubility. Okay, but remember, we can't do that because it's a common ion question. Okay, so in a common ion question, I suggest you make the Rice chart. Okay, so remember, those KSP shortcuts come from making Rice charts where both ions start at 0 in terms of how much is dissolved. Okay, in a common ion question, one of those ions doesn't start at 0. So make the Rice chart so you can organize your information correctly. But regardless, when you solve for x, it's the answer. It's the molar solubility to the question. So we're going to make our Rice chart. We're going to get our equilibrium concentrations in terms of x. We're going to plug those into the equilibrium expression. When I solve for x, it's going to be the molar solubility of the compound. Okay. So here's our reaction. Again, if it was in pure water, this is 0 and this is 0, and that's how we come up with our shortcut. But now this is not starting at 0, it's starting at 0.1 because we had a 0.1 molar solution of aluminum chloride. So our initial concentration of aluminum is 0.1. Our initial concentration of sulfate is 0. The reaction has to shift this way. We need a little bit of sulfate to get to the point of saturation or to get to the equilibrium. So we're going to plus on this side. So plus 2x for the aluminum because its coefficient is 2, and plus 3x for the sulfate because its coefficient is 3. Okay, so at equilibrium, the aluminum concentration should be 0.1 plus 2x, and the sulfate concentration will be 3x. We're going to plug those in the expression, right? So this is the aluminum concentration squared and the sulfate concentration cubed. Okay, now we know that the reaction has to shift this way, but it's not going to shift a lot. So we know x is going to be really, 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 really small. 2x is going to be really, 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 really small. In fact, it's going to be a lot smaller than 0.1. So what we're going to do is 5% rule the 2x, okay? And so we simplify the expression into 0.1 squared times 3x cubed, okay? We know the KSP value from our final answer of the original question. So we'll say KSP equals this. If we solve for x, it's the molar solubility. So x comes out to be 0.0042, which is 4.2 times 10 to the negative 3. Molar solubility needs units, and it's molarity, moles per liter, or capital M. Okay, and that's our answer. Okay, and notice it did go down, right? We went from 0.01 to 0.004. So it got less soluble in the presence of the common ion. Okay. All right. So those are all the answers and kind of a good explanation of how to do everything. Okay. So, if you decide to retake it, which I strongly suggest you do, that's how you do it. And it's going to be similar. It might be different. It might be different ratios of ions. So make sure you know your KSP shortcuts and all that stuff. But it's not difficult. We know all the concepts. It's just bringing them all together, making those connections. Okay. So good luck reviewing for your Unit 4 test and hopefully preparing to retake this lab quiz. All right.